Hello everyone, it's 4th of December 2025, Thursday, 1:30 a.m. here. I'm Dr. Priyanka Chaudhary, an ophthalmologist. In this video, I'll be talking about the nodal point, its definition, its location in the human eye, and its clinical significance. So nodal point is one of the cardinal points of the lens system, and we know that according to Gaussian, for a thick lens system, there are 6 cardinal points which lie on the same line, that is optical axis or the principal axis. So nodal point for a thick lens system, there are 2 nodal points. For thin lens system, there is 1 nodal point, and it coincides with the optical center. So what's the difference between optical center and the nodal point? The optical center, it is for thin lens system. The optical center is that point through which when the rays of the light pass, they remain undeviated. That's the optical center. And the optical center for thin lens, it coincides with the nodal point, and optical center, it coincides with the nodal point and the principal point for a thin lens system. But it doesn't coincide with the geometrical center of a lens unless it is perfectly symmetrical lens from an ideal sphere, taken from an ideal sphere. That time it coincides with the geometrical center of the lens. So that is in case of a thin lens. For a thick lens system, the optical center concept is replaced with nodal points, 2 nodal points. These 2 nodal points, the angular deviation when between the incident ray and the refracted or emergent ray, the angular deviation with respect to optical axis is 0. But there is a linear displacement, and I'll explain this concept using my handwritten diagram here. For a thin lens system, this is a perfectly symmetrical lens taken from an ideal sphere here. It is a thin lens. This is center of curvature of a lens. That is the center of the sphere from which the lens is taken, and this is the geometrical center of the lens. The line joining the center of curvature of a lens, that is the center of a sphere from which it is taken, that center, the line joining this center with the optical center, the center through which when the light rays pass they remain undeviated, that center A. In this case, it will coincide with the principal center and nodal center also. In this ideal case where it's a thin lens, it is perfectly symmetrical, taken from an ideal sphere. In this case, the geometrical center, nodal point, principal center, and optical center, they lie at the same point. Here it's A, and the line joining the optical center with the center of curvature of the lens, that forms the optical axis AC. It forms an optical axis. And optical axis actually, the focal points, principal points, nodal points, they all lie on the optical axis. Now this is my handwritten diagram explaining what these nodal points are in case of a thick lens system. Now in case of a thick lens system, the concept of optical center is replaced with these 2 nodal points. Now optical center is that center in the lens system through which when the rays of the light pass, they remain undeviated. So in this thin lens system, you will see this point A, it coincides with the geometrical center. Optical center doesn't necessarily coincide with the geometrical center of the lens unless it is perfectly symmetrical lens coming from an ideal sphere. Like in this case, the optical center is coinciding with the geometrical center of this lens. It also coincides with the nodal point and the principal center. Now this A, it represents the optical center. Now what is optical center? Optical center is that center through which when rays pass, they remain undeviated, and as it's a thin lens, there is no linear displacement or lateral shift of this ray. So in this case, angle of incidence will be equal to angle of refraction. So theta 1 and theta 2 with respect to the optical axis AC, these are equal. That point is called as optical center, and it doesn't necessarily coincide with the geometrical center, but this optical center is nothing but the nodal point in case of a thin lens system. Now let us see what happens in case of thick lens. Now in case of thick lens, as it is thick, there is no one optical center. It gets splitted into 2 points, and these are called as nodal points. Now these are not called as optical centers. Now this concept, this terminology gets replaced with these 2 points, nodal points. Now when the rays of the light, they pass through one nodal point, angle of incidence is r1, and then it passes like this straight towards the second nodal point, and the rays of the light, they pass through this nodal point in this direction. Now this angle of incidence r1 is equal to angle of refraction r2, and these rays, you'll see there is a lateral shift, that is, there is linear displacement, but there is no angular deviation of these rays with respect to the optical axis. So these points are called as nodal points. So these are defined depending on what they do to the incident ray and refracted ray. Okay, so again, nodal points are those points where the angular deviation doesn't occur in thick lens system, but there is a lateral shift or linear displacement occurs. If it was thin lens system, it would travel like this, but as it is thick lens, the optical center is divided into 2 points, nodal points. Now these are called as nodal points and not optical centers, because in case of optical center, there is no linear displacement, there is no angular deviation. But in case of nodal points in thick lens system, there is no angular deviation, but there is linear displacement or the lateral shift. The ray would go like this, but it's going like this. The angle is same with the optical axis, but there is linear displacement. It's a lateral shift. It will go like this, but it's going like this, but the angle is same. This angle, these two angles are same. So there is no angular deviation, but there is linear displacement or the lateral shift in rays in case of a thick lens. So these are the nodal points. So I hope you got the difference between these two terminologies, optical center of the lens system and nodal points. Okay, there is no angular deviation in both, but there is linear displacement or lateral shift in case of a nodal point, because nodal point is, this is the term that is used in case of thick lens system, and optical center, it is for thin lens system. We don't use nodal points and principal points usually for the thick lens because they coincide with the optical center, and optical center doesn't necessarily coincide with the geometrical center of the lens unless it is perfectly symmetrical and taken from an ideal sphere. So that was about the definition of the nodal point, and I have explained it nicely, I see, with my handwritten diagrams. Now the clinical significance of it. First, I'll talk about the location of the nodal point in the human eye. Now human eye, see, it's a very complicated system. It has cornea, it has lens, has nucleus, and again cortex. So each thick lens system has its own pairs of cardinal points. The cornea will have six cardinal points. Then lens nucleus has 6 cardinal points. Then lens cortex has 6 cardinal points. And even these are not the surfaces with lens systems with, you know, symmetric or very uniform, having uniform refractive index throughout their structure. No, it is not like that. So, but you know, for mathematical calculation and for simplification, this human eye system and human eye model, it is oversimplified. That is called as reduced schematic eye. Schematic eye is that eye, that model of the eye, or that diagram, that model of the eye that explains the optical properties of the eye, defining its cardinal points. So in case of a reduced schematic eye, we take it as one principal point, 2 principal points, average is taken as 1 principal point, and 2 nodal points, average is taken as 1 nodal point. So for oversimplified schematic human eye, reduced schematic eye, that is called as. So in this diagram here, you'll see there is a nodal point in the human eye that is 17 mm away from the retina, that is the posterior pole. Now from where it is taken, it is the posterior pole. It is actually that point on the retina where the optical axis intersects. So that point, it is 17 mm from that retinal pole, and it is 5.5 mm away from the cornea. Now which point in the cornea? Cornea is like this much, so from this point, this point, this point, it is the corneal pole. Corneal pole, it is that point on the cornea through which the optical axis passes to the cornea. It is point of intersection of the cornea with the optical axis. And corneal pole, it usually coincides with the corneal apex. Corneal apex is nothing but it is the steepest point of the cornea. Steepest means it is that point on the cornea with the maximum refractive power. It is the steepest point on the cornea. So corneal apex and corneal pole usually, they coincide, and optical axis, it passes through the corneal pole and corneal apex, because they usually are said to coincide with each other. So that was about the location of the nodal point of human eye. Now clinical significance. What's the clinical significance of the nodal point of eye? See, nodal point of the eye, it is used to define the visual angle. Visual angle is nothing but it is the angle subtended by an object in the visual field at the nodal point of the eye, and it is measured from the side of the object. In this diagram you will see it is measured from the side of the object. I'll be talking about the visual angle and how it is measured. It is measured either in radians. In case of human eye, it is measured in arc minutes and arc seconds because it is that small. Even degrees or radians. Then another unit is degrees. And then there are minutes, and then there are seconds. So 1 degree means 60 minutes, and 1 minute means 60 seconds. This is how we measure the visual angle, and what these units are and how these are correlated with each other, how to convert radians into degrees and degrees into minutes and minutes into arcs, that I'll be describing in detail in the chapter visual acuity. Yeah, I'm going to make a video on visual acuity. In that video I'll be talking nicely about the visual angle. So this nodal point, it is useful to define the visual angle, and it is measured from the side of an object. There is object side and there is retinal side, image side. Object side is in the visual field and image side is on the retinal side of the human eye. So what is the visual angle? Suppose this is the object, so, and this is vertically placed in the visual field. So vertical edges, the light rays coming from the vertical edges, vertical points, vertical edges of the object, what angle they subtend at the visual or at the nodal point from the object side, because there will be angle on the retinal side also, but we are not talking about that thing. This angle on the side of the object, that angle is called as visual angle. And why it is important? Because it determines the size of image on the retina, size of that object image on the retina. If the size of the object is more, then the visual angle will be more, and its image falling on the retina will be more at a fixed distance from the eye. If it is small object, then smaller visual angle at a fixed distance from the human eye. But if it is the same object and its distance is closer to the human eye, then visual angle subtended by it will be more, and it will look bigger when it's closer. Suppose it's closer to my eye, so it's looking bigger. If it goes farther away from my eye, its size becomes smaller. For example, number plate or a car that's going away from us, we'll see it's getting smaller and smaller in size. It's actually, in reality, its size is same, but it seems it's getting smaller and smaller because it subtends or it makes smaller visual angle as it goes farther away from human eye. So as it subtends smaller angle as it passes away from human eye, we perceive it as it's getting smaller and smaller, and it's very important even to judge the distance of the same object from human eye, from us. So that's the significance of the nodal point and the visual angle. And another use of the nodal point is, from this point we can, from the formula height 1 upon distance, suppose this is the nodal point of the human eye, this is object, and then this is the retina. Now this is the visual angle, okay, and this is the distance. Suppose this is the distance. At what distance? It is at distance that is called as base 1 from this nodal point, and its height, suppose this is the nodal point. And what's the distance from the nodal point? Here from down you'll see, from its lower edge you'll see this is the nodal point, and from here we'll see the distance d1. Okay, d1 and h1, this is the height, vertical dimension of an object. This is h1 and this is d1, and this is the nodal point. Draw a perpendicular line down and this line. So this is the distance from the nodal point of an object in the on the side of object, it's visual field. So this is the d1, this is h1, and its size that it will project onto the retina, that image size will be h2, suppose h2, and that distance of image from the nodal point, that is 17 mm. We know that distance, that is 17 mm. So this h1 upon d1 is equal to h2 upon d2. This d2 we know 17 mm. So in case of the reduced schematic eye, according to reduced schematic eye with power 60 diopter, okay, so with this location and 5.5 mm from the cornea, because we are measuring the distance, we will need we know the distance of an object from the cornea, but we don't know from the nodal point. So nodal point and the cornea distance is 5.5 mm, and this, what is that corneal point? That is the corneal apex or corneal pole through which the optical axis passes through. So from this formula we can calculate the size of visual scotoma. If this size of retinal hemorrhage is this much, so how much will be the size of scotoma in the visual field? That we can determine from this formula, that is height 1 upon base 1, height 2 upon base 2. So that is the clinical significance of the nodal point, to determine the size of visual scotoma, or vice versa, to determine the size of the retinal scar or retinal hemorrhage, localized retinal pathology. So that's the clinical significance of nodal point. I hope you like this video, because we think that why we should understand the schematic eye, and why there are so many types of the schematic eyes, and what are these points, and what is their significance, why we should learn these things. You should learn these things because it really has a practical significance, like this I talked about. Also to for research purposes, and to develop new technology, new lenses, and even spectacles and glasses, magnifying glasses or spectacles, contact lenses, and newer technology. We need to know these cardinal points of the human eye, and even the visual angle, what is the effect of that vertex distance also, and how it affects object size. It's very, very important. For these things you should know the cardinal points of the lens system, and how these are applied to the human eye. And it's very, very important to use this cardinal points knowledge to understand various optical aberrations in the human eye, be it higher order aberrations like fourth order is spherical, then third order is comma aberration, then lower order are these myopia, hyperopia and astigmatism. These are the aberrations. To understand these also, we should have the knowledge of these cardinal points overall of the lens system, and then their practical applications it should be applied on the human eye, and how newer lenses we can develop using these cardinal points, and yeah, and the schematic eye. And that's why we should understand the schematic eye also, how these cardinal points are used to define the optical properties of the eye and how these are located. So I'll be making video. First I'll be making video on visual acuity, then color vision, then contrast sensitivity, then schematic eye, and then axis of human eye and angles of human eye, like angle kappa is very important, because the visual axis and the optical axis, they don't coincide. Why it's important? Any object, any lens system is there. For any lens system, the object should be aligned with the optical axis, because the focal points they lie on the optical axis. But in case of human eye, the focal points, they don't lie on the visual axis. The visual axis is the point, visual axis is the line connecting the point of fixation with the fovea, and fovea is we want the light rays to be focused on the fovea and not the focal point of the optical axis, because our brain is trained our brain learns and perceives the highest image quality when it falls when it is focused on the fovea and not on the focal point of the optical axis. So this is very important. That's why we need to define the visual axis that works like an optical axis in the human eye. And this optical axis, it's very important to define the relationship with the visual axis. Why it's important? Because of the comma aberrations. In the lens system, what happens when the lens system is not aligned with the object, and the object here, when object is there along its optical axis and its image falls on the focal point that lies on the optical axis, its image quality is, we get the better picture quality. But when there is an object, but there is another object, but this optical axis of the lens system, it is not aligned with this object that is present peripherally, that is not aligned with the optical axis, the rays of the light also get focused on the this focal point, but at various focal points, not exactly at one focal point, but at various points, and that will give rise to the comma aberration. The image quality is not very good, it's a blur, and it is like a comma, and the tail of which either seems to be going towards the optical axis or away from the optical axis. So that is comma aberration. But in human eye, we perceive the object image best when it is focused on this fovea and not this point on the retina where the optical axis coincides, and where the focal point of the optical axis of the visual system, human eye system, should fall, like on not here. So how it's going to affect the optical aberration, how it's going to affect the comma aberration, even the spherical aberration and different aberrations, because we define them in other lens system with respect to the optical axis. But this visual axis is there, which in the visual field is projected nasally and superiorly to the optical axis, 5-degree nasally, and in case of this left eye, 5 degrees nasally, and 2 to 3 degree, 1 degree vertically, superiorly to the optical axis. And that's why this relationship is very important, and angle kappa is also very important. And the importance of these axes, these angles, it's very important in refractive surgeries, because the eye is not a centered visual system. The optical axis, it doesn't lie with the visual axis, and this is the fovea where the light rays need to be focused. So how to manage in between, how to reduce the aberrations, taking these things into consideration, and even the entrance of the pupil, what is that, line of pupillary axis, that also doesn't coincide with the visual axis. There is also an angle around 3 degree or 4 degree angle in between these two. So it's very, very important to understand these relationships between various axes, because center of pupil, if the light ray is passing through the center of pupil, it is an aperture, so there is a diffraction happening, and we can minimize the diffraction, but we cannot completely eliminate the diffraction, taking into account the optical wave properties, wave-like nature of light. So diffraction is just a bending of light, so the image that we get is not the point image but the spread out image because of the diffraction. So all these things, if you want to understand the aberrations, different aberrations, and if you want to understand this visual acuity, visual angle, and size of the visual scotoma, to understand all these things, we should know nodal points and other cardinal points, even to define different axes of human eye and different angles, because during refractive surgeries also, during cataract surgeries also, where the lens needs to be centered, it's along the visual axis and not always along the entrance of the pupil, especially when the angle kappa is more, visual angle is more. So it's very, very important that I'll be talking about it in detail when I'll make a video on visual axis and angles of the human eye. So that was all about the nodal point. I hope I have cleared the concept of the nodal point in the lens system and how it's different from the optical center and principal center. And principal center is nothing but it is that centered in the lens system where the principal plane and the optical axis, they are perpendicular to each other, and the point of intersection of these is the principal point. So principal point is that point through which the rays of the light appear to be refracted. So it's not that point where the rays of the light, they don't refract. No, it is the point where the rays of the light, they refract, they undergo refraction, because it lies on that plane of the refraction. But as it lies on the optical axis, any light waves passing through the passing along the optical, any light rays passing along this optical axis, they remain undeviated, and any light rays which are parallel to the optical axis, they will converge at the focal point. So I have already discussed all this in this video I have made and posted recently, that is on the cardinal points of the lens system and human eye. You can go through it. I'll put that link in the description box of that video on the cardinal points of the human eye. This was all about the nodal point, its definition, its location in the human eye, and its clinical significance. I hope you like this video. Bye. Good night.